Okay, so although I have altogether 4.5 hours, the topic is a bit sort of wide. So I'm not exactly sure if I can really go through all of them, and especially Sun-chan wanted me to talk on primordial black holes. I'm not exactly sure whether I arrive at primordial black holes, but in any case, I try. But in any case, if you have any questions or some things you don't understand, or maybe if you find some mistakes, I make many mistakes in slides as well. So you can please point me out. Okay. All right. So let's just quickly start. As you all know, that the inflationary universe scenario was introduced to in the original intention probably was to solve so-called some fundamental problems of the Big Bang cosmology. One of them was a horizon problem, which means that if you go back in time, in the standard sort of a decelerating universe, the size of causal horizon shrinks much faster than the expansion of the universe. So in going back, so it's a contraction of the universe. So this means that in the beginning you have infinitely many causally disconnected regions, and you don't know why you have some coherence over those regions. So sometimes people call it a homogeneity problem, and some people actually say that the inflation solves homogeneity problem. Well, this is one thing maybe you can remember. Actually, it's not. Okay, if you want to solve a homogeneity problem, then you have to start with some inhomogeneous initial condition and show that this inhomogeneity decays out and everything becomes smooth. Yeah. But this has not been shown generally. There are some examples, numerical simulations and all these things, but this has not been, there's no clear proof of under which condition you can get homogeneity. So here I assume homogeneity. But the whole point, and which is the most important point of this inflation model from the modern point of view, is that this homogeneous universe, which expands fast, can give rise to the seas fluctuations for formation of galaxies, stars, and planets, and us. Yes. So everything comes from some fluctuations, and you need a fairly large, say, long wavelengths fluctuations, which are on scales much greater than this each causal patch of causal regions. So this is, you can call it a horizon problem, and you can solve it with the inflation. Anyway, so this is the sort of a schematic sort of explanation of the horizon problem. So as I said, I start from a homogeneous universe. So I don't explain homogeneity, okay? Homogeneity is an assumption. And in this homogeneous universe, and if you just consider the expansion of the universe, and let's just for the moment forget about curvature of the space and assume that your three-dimensional space is flat. Then the acceleration of this expansion rate, a scale factor, is given by this minus 4 pi g over 3 times rho plus 3p. P is the pressure, rho is the density. And if this rho plus 3p is positive, because of this negative sign, the universe always decelerate. This is because of what we all know, that the gravity is attractive and universally attractive. And this combination actually appears almost everywhere. This is, in some sense, you can call active mass, effective mass of gravity. It's always given rho plus mass density, maybe I should say, rho plus 3p. Okay, and then if this is the case, if you just assume very simple-minded sort of a expansion law, then if you have say a negative sign here, which means that second time derivative is negative. So if you just assume a scale factor to be t to the power of n, and n plus 1 is negative, which means n is less than 1. Bigger than 0 because we assume expansion, by the way. Anyway, so this means, as I said, the expansion in the universe is slower than, say, free expansion, which would be the case if n was 1. Yes, then it's a sort of just free expansion, but with no accelerations. But you have actually deceleration, and the problem, I mean, and the horizon problem occurs because of decelerating universe, and which can be most easily seen graphically by drawing so-called conformal diagram. And this is another thing maybe you can learn a bit today. The conformal diagrams is a diagram which is conformal to the original metric or any metric. So you can do the conformal transformation. Conformal transformation is some transformation in terms of some factor, some function in front of some metric. And this metric actually, if you introduce so-called conformal time, then is conformal to a flat space. And the important thing is that this ds square, sine of ds square, yes, if a square is positive, which we assume, is this sign is, if this is positive, that means that this sort of Minkowski space, a four-dimensional distance with ds square will also be positive. And this is negative, this is negative. If this is 0, this is 0. So your causality doesn't change under conformal transformation. So when you talk about causality, it's best if you draw a conformal diagram to make everything into some compact regions. And this is exactly what I'm doing in some sense. But anyway, so important point is our universe, let's assume that there are no spatial curvature, is a conformal to a flat Minkowski space. Now, so you just draw a space and time, space-time diagram, Minkowski space-time diagram, and which tells you the causality of the universe. The whole point is that if this eta, conformal time, is indefinite to the past, that means that if this eta can go to minus infinity, then you have standard Minkowski spacetime where we don't have any causal problems. You know, any 2 points will be causally connected by some light cone. So there will be no problem. But if A is this power Tn is decelerating, then this integral dt over A integral, this is the definition of the conformal time, will be finite when t goes to 0, which means that you have a finite past. It's not usually people say that you have a horizon problem because our universe is finite in the past. Actually, it's a half right but half wrong. The correct way of saying is that if the conformal time is finite in the past, then you have a problem. And this is exactly what happens. Okay? So if you use the conformal time and go back in time, you end up with some spatial hypersurface where the universe started. Okay? And if you have a finite beginning in conformal time, you will have a horizon problem, causal problem, because light always the size of light cone is finite, and if you go back in time, the size of light cone is smaller and smaller and smaller. So that's what it happens. For example, in a Big Bang universe, you have the very hot Big Bang in the early universe, and that which clears up when the hydrogen atom is formed by electron and proton get together, so-called recombination, and the universe clears up, and we see this clearing up sky at the surface as in those famous cosmic molecular background radiation. But anyway, so when we see backwards in time, then we have this light cone, and we see these points, or maybe actually it's a two-dimensional surface, as you know. but since I cannot draw 2 dimensions here, so it's just look like 1 dimension, but this is a circle, huh? Or the sphere. But anyway, but these 2 points will be totally disconnected if you have a finite past. Yes, and this is the cause of horizon problem. Now, then it's very apparent, at least if you can sort of prolong this. Oh, by the way, this is a nice exercise that, you know, let's say the current time, let's normalize the conformal time. This is because, you know, the conformal time, there's no scale, so you can just you know, take any scale you want. And so let's say this time today is 1, and this is a 0 in beginning of the universe. And then they compute the what this time for the last scattering would be when the universe was like I don't know, 3,000 Kelvin, or, you know, it's the age of the universe was like 300,000 years or something, 300, 400, something like that. Yes, but anyway, that's another. Yeah, you can maybe do it right now because when I'm talking. But anyway, so this is the reason of the the cause of the problem, and then the only, not only, but the simplest way to solve this problem is that just let this theta equal 0 going backwards a little bit more, so that from the beginning the whole entire universe we see can be given within one single causal patch. So this is actually what you do in inflation. So this you cannot do if n is always less than 1. But if you consider some sufficiently long duration of stage where n is greater than 1, which means that the accelerated expansion. If you have accelerated expansion stage in the early universe, then, for example, if this actually happens to till when t goes to 0, then it's trivially, you know, it can be trivially seen that this integral goes to infinity. So, so you have unbounded sort of a beginning. Although the real time may, you have real time, I mean the cosmic standard proper cosmic time, may have finite past, but a conformal time will be infinite. And if the conformal time becomes infinite, you solve the horizon problem. Okay? So in any case, you know, it doesn't have to be infinite, but you just prolong this stage longer so that you have a whole our observable universe within one causal patch. And this is exactly how the inflation works. And in the case of inflation, actually n is very, very large, much larger than 1. Yes. Now another thing which is usually called a flatness problem, that our current universe for some reasons very, very flat. I mean spatially flat. And usually you would expect our universe to be either, you know, a closed. I mean, again, I'm assuming homogeneity. So for homogeneous universe, only option is whether the universe is closed, like slit sphere, or flat, or open, in which case you have a hyperbolic geometry. And in any case, if you have the standard matter, and like again, when the case when n is less than 1, for example, then those universe, when they are closed, they can actually collapse in a finite time. And if they are the curvature term, spatial curvature is of the same order of expansion rate. By the way, yes. So this is, maybe I should have drawn the most important equation in the universe. This is the Friedmann equation, and oh sorry, it's square, and so this is 8 by g rho divided by 3. But the important point, this essentially is a four-dimensional curvature. In some sense, this is the expansion rate. So it's, in some sense, this is a curvature towards time. So time-like curvature. I mean, it's a bit odd way of saying decomposing the curvature, but then this is the space in spatial curvature, and if everything's set up in a sort of a natural or maybe a democratic way, then there's the curvature towards time-like direction would be of the same order of the spatial curvature. And if this is the case, if k is positive, which is the closed universe, it collapses within the Hubble scale. So if you go back in early in the universe, let's say if you consider some Planck time or something, then the universe just collapses within Planck time. So we won't have a current universe. If this is negative, then again within the same time scale, the universe would become completely empty, because the effect of curvature scales like 1 over a square, while the density, for example, if you consider the radiation, it's 1 over 8 to the 4th. So as soon as the universe starts to expand, this decreases very rapidly, and this starts to dominate, which means that essentially you end up with flat spatially, it's a Minkowski space. So nothing, and which happens within a blink of time. So we don't get the current universe. This is the so-called flatness problem. And put it the other way, actually, so if you consider some matter inside this curvature radius, then the total entropy within that radius is a natural sort of a unit would be order 1 or maybe 100 or whatever, but not so large. But it turns out in our universe, at least, because maybe actually the spatial curvature is really 0. In that case, of course, it's infinite. But just assume that our universe has some finite curvature radius, which is much greater than what we see in our universe today. But in any case, then you compute the number within that curvature radius, we find that it's much greater than 10 to 87 or 10 to 90. So this is a huge number. Because nowadays people talk about those number of vacua, which is 10 to 500. Now, these days, maybe they say 10 to 1,000 or something, which is really, really, really huge number. Compared to that, this is nothing, but still, it's good. And by the way, yes, entropy is a logarithm of the number of states. So actually, if you just count the number of states, this will be on top of the exponents, then you win. I don't think there's any other bigger number than that. But anyway, so such a number must be explained. It's a very unnatural to think such a number existed from the very early universe. The only, maybe it's not only, sorry, but most sort of a plausible solution, again, is to have some kind of a huge entropy production in the early universe. And this, again, is given by the inflationary model. So this motivates a lot of why we think about such a model. But of course, you have to realize in some way, by some concrete model, so that you can compute things. Now, so in the historically, there are several sort of different models which failed and so on, revived and so on and so forth. But so let me just give you one simplest typical model, which is called single field slow roll inflation. And you just assume, this is assumption again, that in the very, very early universe, there was some scalar field which dominate our universe. Again, I assume homogeneity from the beginning. Okay, then for some reason it was homogeneous and the scalar field dominated the universe. Then if you if you compute this rho plus 3p, which was the active gravitational mass, and we want this to be negative, so if you compute this, then you find this is two times the kinetic energy minus potential energy. So in any case, if the kinetic energy is much, much smaller than potential energy, then this rho plus 3p would be negative. Yes, and so this is the condition for the universe to be accelerated. and which can be fairly easily actually realized if you assume the universe is dominated by scalar field. This is the a very important point. Now, of course, you have to prepare some initial condition, and there are many ways to do. And one sort of typical, or I mean, in some sense, way to hide the problem of initial condition is so-called chaotic inflation models, where you assume that our universe was chaotic in the very, very early universe, and for some reason, certain region of space started to expand, and then which you assume this is slightly below the Planck energy scale, and so on and so forth. And in this case, you find that if the second derivative effective mass of the potential is much, much smaller than Planck scale, then if you assume the initial energy scale would be Planck, then scalar field value would be much greater than Planck. There are some problems, so-called Lies bound problems and so on and so forth on this sort of inequality. But here I don't go into details. I mean, there may be a problem, it may not. It is essentially a problem of quantum field theory and not the problem of inflation. So I don't touch it. But anyway, so this is the condition if you assume the initial vacuum energy, the energy density of the universe is nearly Planck. Now, in this case, if you assume this is nearly Planck, then Hubble expansion rate, of course, is of the Planck scale, while the potential, as I assume that the potential, so effective mass of potential is much, much smaller than a Planck. So if you, for example, simply assume, let's say, V equal m square phi square, then this is just m square phi. So this will be a sort of a equation for damped oscillation if m was great, larger than this friction term. But the assumption was that this mass scale is much smaller than Planck scale. So which means that actually this potential force turns out to be very, very small. So in this case, you have so-called overdamped system, where actually instead of this damped oscillation, you just slowly goes down the hill and without any oscillation. So in some sense, you approach some finite limiting velocity. It's like when you have some rains dropping from the very high height, and if there are no air or anything, no friction, then it accelerates rapidly by the gravity. But because of the friction, you have some terminal velocity, and that's why we, even if we are hit by a rain which came from very high in the air, we don't die. I mean, if there are no air, then a drop of water would just kill us. But anyway, that's different from inflation, by the way. Here, so in this case, you can compute the terminal velocity in terms of the friction. So you just ignore the second time derivative and compute the phi dot. And this terminal velocity will be given by the v prime over 3h. And this is called the slow roll approximation. And if you assume this, then you can easily compute, under this condition, if you compute the secondary derivative, and you confirm that if in this case you will have a very small acceleration. So you will actually approach this terminal velocity. Now, another thing which is most important is that, actually this is more important, is that if you compute this time derivative of expansion rate, then it is given by this rho plus p. And in our case, since rho is 1/2 phi dot square plus v, and p is 1/2 phi dot square minus v, so potential disappears and you get this twice the kinetic energy. So, and you have this minus sign. And if you consider the ratio of these two, which essentially gives you the change time change rate of the Hubble expansion rate per Hubble expansion time. Okay, so if this is small, then it means that the expansion is almost constant. Expansion rate is almost constant, which means you have almost exponential expansion. So this will be a condition. Then you can easily see that if you take the ratio, this ratio, the smallness ratio will be satisfied if phi dot square is much smaller than v. And actually, this was the original a condition for our universe to be accelerated. So if phi dot square is much smaller than v, then you can, in the reading order approximation, ignore this phi dot square contribution to h, and you can just assume h square is given by v over 3 m Planck. By the way, this m Planck is the 1 over 8 pi g. I'm including 8 pi in this Planck definition of Planck scale. Anyway, so then you have really exponential, almost exponential expansion. So this is the condition actually for our universe to be in inflationary. So this is sort of a secondary. Actually, you don't really need slow roll. I mean, of course, you have to do some tricky sort of introduce some tricky field, or as you all know, here's this famous Professor Slava Mokhov now busy with his phone. Yeah, but he's the one of those. Yeah, I retaliated. He's the one who introduced so-called K inflation, where you don't actually need any slow roll, but you configure the kinetic term in an arbitrary way. You can do whatever you want to do. But anyway, so here so in that sense, this is not exactly what necessary condition, but in some sense sufficient condition. This is the smallness of so by the way, so this h dot over h square is usually given but with minus sign is because this is h dot actually is always, as you could say, always negative. So this one is you put minus sign to make it positive, and this is usually called slow roll parameter, but it's nothing to do with the slow roll. It is the parameter which defines the inflation. And if this epsilon is smaller than 1, you have inflation. Okay, so this is the most important condition. But in the standard case, with the standard sort of field, with standard potentials and so on and so forth, then actually, if this is satisfied, this automatically means phi dot is small, and which means essentially that your slow roll condition is satisfied. Okay. Anyway, so now you have all these different parameters which comes in, and the parameters. There are sort of confusions in the notation here. So in order to avoid this, so I introduced this eta v and epsilon v, which is solely given in terms of the form of the potential, and epsilon v is essentially given by this v prime square over v square, and this is almost equal to epsilon when you have a slow roll inflation. This eta is there are some confusions. So here this eta is defined in terms of epsilon dot. So it's the derivative of the slow roll parameter and epsilon. But this is not so useful. I mean, it is important, but it's not so useful in many computations. Mostly, more useful thing is so-called, here I call eta v. And some people just call this eta. And because of this, you get really confusions. And sometimes, well, even I have to confess, in some paper, first I wrote some formula and with this confusion, so the formula was completely inconsistent later. I realized this after somebody mentioned this to me. But anyway, so I corrected it in the published paper, but you can make mistakes. But anyway, so this eta v represents second derivative and in units of Planck scale. And if those two parameters, which sort of characterize the shape of the potential, if those two are small, then you have slow roll inflation, single field slow roll inflation.
So why do you put V as a subscript?
Sorry?
So that is another parameter. So you call it eta of V.
Yeah.
What is this V?
Potential. Potential, yes. Epsilon V it's just the eta given in terms of potential. And yes, many people just call this eta.
Right.
Yeah. But to make it clear, because some people call this eta, and there's really a confusion. It's big difference between these two. So I use this. So I put V if I want to compute. So this is when people talk about so-called eta problem. This is this eta they are talking about. Yes. Anyway, the whole important point is that these two. Sorry? Sorry?
This epsilon.
Yeah.
You define by derivative over time.
Right. And if you use this slow roll equation motion, then it is given by this. And which is given by the solar potential. That's why I put V. So this epsilon and this epsilon V is almost equal in slow roll inflation. But in other models, again, these can be different, quite different. So you have to be careful. Yes.
Yeah, you need to make an assumption for potential domain.
Right. Yes. That's right. I mean, this equation is most important. Yes. Right. Anyway, sorry. So another important is that these are not necessary but sufficient conditions. Okay. Yeah. The only necessary condition actually is this. Yes. And everything else can be violated, but you still have inflation. But of course, it's not so easy to think of such a model. But still, the only important condition is this, and everything else is a sort of a sufficient condition for inflation. That's one thing maybe you should keep in mind. All right. Now another thing which is in this slow roll inflation, on many inflation models, one of the most important sort of quantities is so-called number of E-folds. And actually, we do need some certain number of E-folds, 50 or 60, to solve this horizon problem I told you, a few minutes ago. So, but this number of E-folds, when you count, actually you count from certain time until the end of inflation. Or maybe, if we know the whole history after inflation, actually, you should probably count from certain time to today. And this tells you how much, how expansion we went through, from certain time in the early universe. So, well, this is sort of standard way to parameterize things in cosmology, because we know we are here now, but we don't know the initial condition. So if you don't know the initial condition, it's not so wise to start from initial condition, because if you change the initial condition, everything changes. But if you start from today backwards, then until the point where you know the physics, then nothing changes, and beyond that you may change, but you just add some more things. And in cosmology, actually, usually we use so-called redshift factor, because in the early universe you have the larger redshift. Essentially, number V for this is the logarithm of that redshift. Yes. Okay. So in the exponent. But anyway, so you define this from some time t, and here, since we don't really know what the early universe history, our origin of time will be the end of inflation. So from the end until the end of inflation, you compute the number of E-folds. And this tells you how much expansion you went through during inflation, which is meaningful for our universe. Yeah? Then if you because this is another important point, because of this relation actually, and as long as the V dot V prime is non-vanishing, then the phi and time, this is d phi dt, So it can be, phi can be considered as a clock time. Yes, I mean, it's monotonic. So if time is monotonic, as we know, and if this is, if v prime has a definite sign, then again phi is monotonic. So you can assume phi to be a time, and so change dt to a d phi, and then you have phi dot, h over phi dot. Now this can be, then you use the slow roll equation motion, this equation motion, and replace phi dot by v prime over 3h. Oops. Oh yeah. And then you have a b prime is h square over b prime, and h square will be then given by, again, oops. Well, as I said, the potential dominance of the energy density means that h square is given by the potential divided by Planck scale. So if you insert that, then you get essentially the integral of d phi of the v over v prime, and because of the negative sign of phi dot, you change the upper and lower sort of integration limit. So the lower limit will be the value of a scalar field at the end of inflation, and the phi will be the some initial moment or some moment in the past. So for example, in the very simplest case, which unfortunately this model is now observationally excluded, but since it's so simple and it essentially contains almost all how to say important features of the inflation, so let me just use this here. Then this can be easily computed, and you see that this will be given by phi square by phi f square divided by Planck square. And if you want n to be large enough so that you solve the horizon problem, and since this is already fixed, and essentially we can easily see that this is a order Planck scale. So this final condition would just give you order 1 contribution. So if n is to be very large, like 50 or 60, it will be dominated by this phi, the value of phi at the time when the number equals n. So this is given by this formula. And you can just, given your model of potential, you can easily compute this relation at any time. It's very easy computation. Anyway, so this is a number of efforts, and we will see later in this afternoon that actually fluctuation, if you consider fluctuation this number of efforts, you immediately get the amplitude of fluctuations you want to compute. Anyway, so this is kind of numbers you would have, for example, in this case, and sorry. Of course, as I said, the observation this is almost excluded, so it's not so good to still use this for this model, but for inflation model. But still, effectively, this gives you the rough sort of a picture of what is going on in the early universe during inflation. And the whole point is that the energy density or the energy scale of inflation, if you assume to be so-called a grand unified scale or whatever, it's 10 to 15 GeV, it's 10 to 16 to 15 GeV. And if you just assume the number of people to be greater than 60, then you can see that you can solve this horizon problem. Again, if you go back to, remember this conformal diagram, then yes, this is your homework. If you compute this, then you see that at least if you just assume these two, then your light cone will cover the entire universe today. Okay. Anyway, and in any case, in this sort of a simple model of inflation, as I said, the end of inflation is essentially given by the Planck scale, and after that, you do need to reheat our universe, and so that you produce oh, by the way, so scalar field, of course, if it is just slow rolling homogeneously, it doesn't have any entropy. So you have to produce entropy to make our universe big, and this can be given by this reheating process. And this process is, there are many mechanisms, many sort of ideas or many models, but we don't have any clue of what kind of reheating we had in the early universe. But this, fortunately, not knowing the reheating doesn't affect much of the later universe. And I will come back today, later today about this. But anyway, so for the moment, just forget about the reheating. Assume that we had some successful reheating.
So here you have a lower bound on the number of e-folding, but so as long as it's bigger than 60, we are fine. Or you have also upper bound?
Yeah. If number of e-fold is beyond 60, then even for fairly larger energy scale, it's okay. Yes. I think if you want to go down to a lower energy scale, you can just reduce number of e-folds. But yes. So actually, if you just assume, I mean, this is sort of upper limit. Where if you assume that your inflation was occurring at Planck scale, then the number of e-fold you need would be like 65, 70, somewhere around that. And so if you have number of e-fold much more than that, then you have no horizon problem. Okay. So on this background, we now want to compute the fluctuations. And as I said in the beginning, this is the most important part of which has some important predictions of inflation. As I said, I mean, homogeneity doesn't work. I mean, we do see a fairly homogeneous universe today, but inflation cannot explain homogeneity, as I told you. And flatness maybe, but it's just single sort of fact. But if you go into the say fluctuations, then you have various information, like amplitude fluctuations, spectrum, and maybe running, or maybe some other features, and so on and so forth. All these, the fluctuation contains very rich information. That's why fluctuations are so important. Now, let me assume that simplest case, that you have the Einstein gravity plus some minimally coupled standard scalar field with some potential, and on this this is exactly the so on this slow inflation model I discussed. Now then on this background you just expand this to the second order to consider some fluctuations, and when you consider fluctuations, there appears usually three types of perturbations called scalar type perturbations, vector type perturbation, and tensor type perturbation. Essentially because the Einstein equation has two indices, tensor indices, and so that's why you could say that everything is tensor. But so here what I mean by scalar is scalar with respect to three-dimensional surface. You have we assume the homogeneity, so we have homogeneous three-dimensional space. And for simplicity, let's just assume the flat space. You can introduce some curvature, but it just gives small additional complications, and it doesn't actually matter much. So let's assume we have essentially a very flat, spatially flat universe on which you have some fluctuations. Then on this three-dimensional space, you may have some scalar type fluctuation, actually, which means that you have no intrinsic spatial indices, and you have maybe, if you have one spatial indices, it's a vector, and if you have two, you have tensor. Now, scalar type is the one fluctuations which can be given in terms of some scalar function. Again, it's scalar with respect to three-dimensional space. Here, for example, A, B, and R, and H. Okay, so this A is in front of the time squared. So this is essentially a fluctuation G00 component, and so you can sometimes call it like a fluctuations in Newtonian potential in Newtonian gauge, so-called Newton gauge, or just say that it's a fluctuation so-called lapse function, because it gives you the distance between two hypersurfaces, the time-like, space-like hypersurface. B corresponds to a shift in the spatial coordinates from one slice to the other, so this is called shift vector. And so these two essentially represent the so-called coordinate gauge degrees of freedom. You have, in Einstein theory, as you know, that you have the freedom of choosing any coordinates as long as coordinates are regular. So, but if you change the coordinate, then the quantities seems to change. At least the value seems to change, because if you change the level of coordinate to one to the other, then actually you're evaluating something on some different point. But in the case of fluctuations, you can sort of this is not a very easy part, but okay, let me just draw. I don't know. I hope you can see here, or maybe that side is better, or I don't know.
Maybe that's better.
Yeah, that's better. Okay. Yeah. Oh yes. Oh. Yeah. Okay. So let's assume this is some a space. Yes. Forget about time, and of some homogeneous space, and on which you assume some fluctuations. But of course, real universe may be some fluctuation like this, huh? So this is the universe we want to deal with. But if you do not use some sort of background reference frame, things becomes very difficult. So you assume those fluctuations are defined on this background, which means that if you take some point P, then you have to define the corresponding point on this space. Now, this mapping is arbitrary. This is the gauge degrees of freedom. Okay? Yes. I mean, you can do whatever mapping you want, right? This is the real space, and you want to have some coordinate here, but this coordinate can be chosen arbitrarily. So this is why just giving some fluctuation doesn't tell you much. You have to define what kind of gauge or what kind sort of a correspondence you give for some base point x. Yes, and gauge transformation means actually that if you do the coordinate, again, you can do the coordinate transformation x bar, then this will be, this same point will be called x bar. And let's say this was infinitesimal, so you assume some small deviation from a initial coordinates. Then this x will be somewhere here, and this will be xi. Yes. So in terms of the value here, actually, maybe if you just first define this correspondence and define some fluctuations, then if you use this x bar as a coordinate, but look at some fluctuation values here, actually you are looking at this point, and there will be a difference. So this is the gauge transformation. Okay, and if this is infinitesimal. If it is not infinitesimal, this is just simply a coordinate transformation. But in this case, you don't really have this background, so you don't have to worry much about. But as soon as you introduce some background and define fluctuation quantity on this background, you introduce this gauge degrees of freedom. And in the case of scalar perturbation, this is given in terms of these two variables a and b. So you have 2 degrees of gauge degrees of freedom. Now, and as for the spatial metric, you have 1 degrees of freedom from the longitudinal or the volume factor, which I call R, and another one is sort of anisotropic part, which I call by HT. Yes. well, actually, you can. This decomposition is sort of arbitrary, but this is in the later computation. This is the simplest, so I introduced these two. Now, as I said, so this means actually if you have two sort of well, from the sort of Hamiltonian dynamics point of view, so this three-dimensional metric part actually gives you some dynamical variables, and in our case you have two dynamical variables, but you have 2 degrees of freedom in gauge, so actually you don't have any dynamical degrees of freedom if they are only pure gravity. But if you add scalar field or some matter, then of course this degrees of freedom kind of revives, it becomes alive again. So let's just assume that it's a fluctuation of delta phi to be chi. This is just for notational simplicity. This is just delta phi. Okay, so you have A, B, R, H, T, and chi, 5 variables. And as I said, A and B is this just, corresponds to coordinate gauge degrees of freedom. And this actually represents the spatial curvature, or actually it's a potential, but usually we call it curvature perturbation. And what we call the curvature perturbation actually is a spatial curvature potential. Yes, because if you compute three-dimensional curvature, actually it's given by this formula. So a Laplacian of R gives you the spatial curvature. So it's actually a curvature potential, but in any case, this is a important relation. Oh, by the way, another important relation, as you could see, if the Laplacian R or R itself is time independent, if it is time independent, then three-dimensional curvature actually scales exactly like background curvature, 1 over a square. Yes. So this becomes very important later when you compute things. So R itself actually has no physical meaning, but the Laplacian R is a real spatial curvature. Yes, and which can look like the curvature of entire space. Anyway, and HT, this is a traceless, actually comes from traceless part. It's actually represents the shear of the metric. It's so if you evolve one hypersurface to the other hypersurface, then you have some sort of a shearing motion of the space. It's not so easy to explain, but in any case, this represents that degrees of freedom. So
one question. So what is the meaning of K? Is it wave number?
Oh yeah, that's right. Yes, K. Sorry. So yeah. So here, well, since I skipped the sort of the introduction of the cosmological perturbations, I'm sorry I didn't explain. So Y actually is a harmonic function, and in our case, you can just simply assume this to be the exponential kx. All right. So this satisfies so-called harmonic equation or Helmholtz equation or whatever you call. But so we expand the scalar quantities in terms of these harmonics, and one sort of a simplest choice of harmonics is the plane wave. Yeah. And so you can assume that everything I do from here, I mean I'm sort of writing in general way, but can be just exponential ikx. Okay. And so if you expand in terms of this Fourier modes, then, and of course you have an integral and so on, but since this is a linear theory, you can just focus on each mode by mode. So this is what I mean, yes. And so these are, so now you can forget about all these K-space things, because this I haven't introduced. But anyway, so this is sort of a general way. I guess, I mean, if you assume this is non-dimension, then these give you non-dimensionless variables. Okay, for example, you have the derivative, and this derivative metric is non-dimensional. So derivative of b must be non-dimensional. And if you take the derivative of this, k factor goes away, and so b becomes non-dimensional. So it's just a convention. But anyway, so sometimes I might go back. Yeah, actually later I would go into a Fourier space because it makes computations much easier. But anyway, so this is a sort of a relation between the real space variables, potential variables, to some variables in the Fourier space. Yes, okay? Now, so to consider the perturbations, and in the end we want to quantize the system, so you just expand to the second order. The first order part vanishes because you assume the background equation is satisfied, so you have to expand to the second order. And the second order, actually, I mean, and I'm writing in this form so that it looks much better. I checked the equation yesterday, and I think I didn't make any mistake. Now, yeah, you can check by yourself, okay? Anyway, the important point, maybe a technically important point, is that, so you see all the these lapse function and shift vector to be in combination of with some time variable, time derivative, yes, and so if you combine in this way, the computation of Hamiltonian becomes fairly easy. And yeah, but still, yesterday I again tried to write down the Hamiltonian, and then it took me several hours to realize that I'm making stupid mistakes somewhere, and so it might take you some time, but for smart people it takes only 30 minutes or so. Anyway. But it's another good exercise if you want to do. Yeah. Okay. And the important point, of course. Oh yeah. So by the way, when you quantize the canonical way, that's why you call canonical quantization, is to introduce Hamiltonian, and do the quantization we're using the Hamiltonian equations most. Okay. Or Heisenberg equation, or whatever you call. Anyway. So canonical momentum is just simply given by, as you know, all these variables, time derivative with respect to some time derivative. P chi is the momentum of the chi. PR is the momentum to the R, and PT is the momentum to this HT. Okay, and you have this, and then what you have to do is to solve this in terms of the momentum. So as you can see, this you always have this combination. So it's nice to write in this way. Then you can just solve for this and plug that back into the action to get the Hamiltonian. So this is the at least simplest. Well, maybe there are some better way, but sort of simplest way to do the computation. Then once you do this, write down the Hamiltonian, then you find actually this A and B just remains as it is, and by the way, yes, there's no time derivative of A and B. This is because they are the gauge degrees of freedom, and they are non-dynamical, and this non-dynamical variable gives you a constraint equation, so-called constraint equations, and A and B becomes Lagrange multipliers. Okay, so you have this form. You get the Hamiltonian. This is a bit complicated. Again, you can do your computation. If you're good enough, you can do it within 30 minutes. If you're as bad as me, it takes about 4 or 5 hours, but still, yeah, you can do it within a day. Anyway, so you obtain this equation, and this in front you have this A and B, and you have some variables. Now, since this is second order, this is a linear in variables, canonical variables. For example, for CA is given by this equation, CB is given simply by PT, and these two because this is the Lagrange multiplier, they must be vanishing, and this gives rise to so-called constraint equation. And the first one is called Hamiltonian constraint, second one is momentum constraint. Okay? All right. So now you have 3 variables, 3 momentum, and 2 constraint equations. And actually these constraints are so-called first class constraints, meaning that you have some local gauge degrees of freedom, and which is usually represented by this transformation. If you take some quantity q, let's say q, some of those variables, canonical variables, then take this T, CA, and LCB combination and integral over 3 space, and you take the Poisson bracket. Okay, then this will give you some additional gauge transformation, and this is very easy to see because, well, not maybe easy, but this is how you define the gauge transformation, because as you could see, the Hamiltonian or total Hamiltonian have this ACA and BCB part. Now, depending on the value of A and B, of course, you have different Hamiltonians, so your evolution would be different. But this difference is solely because of different choice of gauge. So this means that if you just plug this Hamiltonian and integral over time, space, so, and you take some Poisson bracket, then you have the time derivative of this, right? You have the time evolution. And time evolution will be different for different value of A and B, but this difference gauge difference. And this difference is represented by this, as you can see. Yeah? Because this is a part of the Hamiltonian. This T is, so the difference between the A plus A bar, for example, if you have some 2 different A's, like A bar and A, well, maybe I don't need it. And then this will be T, yes? B bar minus B will be L. This will be the difference, and this difference gives rise to different evolution, and which essentially is the gauge transformation. So it's a gauge evolution. It's so no physical. So in this way, you can see that if you take the Poisson bracket, you get gauge transformation. And of course, when you quantize the system, of course, you just replace this with a Dirac bracket. But so far, you don't really have to do it. In the second order equations of motion, actually, a classical system and quantum system are completely equivalent. So free motion, essentially. So it doesn't really matter whether you quantize or doesn't quantize. But anyway, so you take so this is, and it's almost trivial to see that Lagrangian, total Lagrangian, is gauge invariant. If you plug the total Lagrangian into this formula, then you get up to the total derivative, the Lagrangian is gauge invariant. This is, of course, the result of the coordinate invariance or the covariance of the original theory, that the original theory is completely coordinate independent. Okay, so and another important thing, yes, is that these constraints, of course, if you transform the constraints to by gauge transformation, it must give you 0, otherwise you have problems. At least we must, and which we call, we must close the algebra. So constraint, a commutation relation between 2 constraints must be proportional to constraint. In our case, since this is a very simple system, actually you just get 0. Yes, and by the way, if it is non-trivial, then you have this so-called Lie algebra type thing, that the constraint, a commutation relation of constraint is equal to constraint. The coefficient is the structure constant. And structure constant actually maybe structure function. Yes, it's not, doesn't have to be constant. Anyway, So this CA and CB constraints are gauge invariant by itself, and so now this is a fairly, I mean, in those simpler systems, this way of a quantizing system is quite powerful. So that I introduced this to you. It's called the Faddeev-Jacquif method, and when I first found it, yes, I was quite impressed because before that I always followed so-called this Dirac quantization procedure, introducing some additional sort of gauge function and so on, and you make sure that your gauge is non-commutative in a sense. You have so-called Faddeev-Popov determinant non-vanishing. Now all this complication doesn't. It disappears in this formula. The point is this. So it's very, very useful, especially for the simple systems. Well, let's solve the let's say we solve the Hamiltonian constraint for some variable. Here, well, if you look at the equation. Well, as you can see, either you can solve for p chi or pr. This looks the simplest, huh? So for the moment, I just solve for p chi, but you can do the same thing for pr. Again, this is your exercise, and then you plug the resulting expression, for example, p chi, into this Lagrangian. Now, I said the CA is gauge invariant. So this procedure is gauge invariant procedure. So if you just plug that into, the important point is that we are writing everything in terms of Hamiltonian, but we're still dealing with Lagrangian. This is the first order form of Lagrangian. So this is the important point. And as long as you deal with Lagrangian, the Lagrangian has this gauge invariance. And you fully use this gauge invariance of the Lagrangian. Okay. Now, then insert that back into the action or Lagrangian. Then also the CB. This is simple. I mean, this is just T. Sorry, but anyway, the canonical conjugate momentum of this shear part of the tensor is equal to actually the constraint. So you just put this momentum equal to 0. And that simplifies things very much. Actually, so since this fact is almost immediately seen from the structure of the original Lagrangian, actually you can just put this equal to 0 from the beginning. That simplifies equations a lot, but that's another story here.
So,
yes?
So could you go back to?
Yes.
So here, CA and CB are gauge invariant.
Yeah.
So that means if I take delta of CA, it becomes 0.
Yeah.
So
This.
same meaning of.
Yes, that's right. So this actually is a gauge invariant combination.
But in the next slide, you choose particular value of CA.
No. So not a particular value. It's just a particular component and solve for this. Yeah. So you have the p chi equals some equation, and you plug that back, or put it in this way. You just plug the constraints into the total Lagrangian. Yes. So you can replace these parts are 0, and you just plug that into this part. And then, but the result depends on which variable you remove. Yes. So if you, for example, solve for p chi, then p chi goes away from your expression. Right. It disappears from the expression. If you solve for pr, then pr disappears from the expression.
So you say CA equals 0.
Yeah.
Is solved by particular choice of P of.
Yeah. And actually, this corresponds to the choice of gauge.
Okay.
Yeah. It depends on what you want, but just do the simplest or maybe easiest.
CA and CR CP are all gauge invariant.
Yeah. So this.
Procedure itself is gauge.
Yeah. That's right. That's why it works very well. Yes. And then you see that in this case, resulting S2 is a functional of these three variables. Yes. But of course, it cannot be. This is a Hamiltonian system, so the variable must be even. And actually, this means that there are certain combination of them which gives you gauge invariant action. Yes, in terms of gauge invariant variable. So this is this statement. Since CA equals CB, which we just plug that back into the action, they are gauge invariant. This is still gauge invariant. If you do the gauge transformation, they remain gauge invariant. So it's and the one variable is, we have too much one variable. Huh? So this must go away. Now in this case, since we just remove the p chi, you can immediately sort of guess that one variable can be absorbed into some other variables to make everything gauge invariant will be chi. And actually this is the case. You immediately see this combination is gauge invariant, and this combination is gauge invariant. And this action is solely written in terms of these gauge invariant variables. It looks slightly different from what we see standard. But now, once you have this, then it's fairly easy. By the way, so P is a canonical conjugate momentum of the RC. And the reason why I put this C is that actually this corresponds to so-called co-moving slicing gauge, where actually, as you see, you solve for the fluctuations, a scalar field, meaning that you assume scalar field is zero, fluctuations are zero. So delta phi equals 0 or chi equals 0, as you could easily see. If you choose the gauge where chi equals 0, this exactly agrees with this. This exactly agrees with this. So these variables are actually defined on the so-called co-moving slicing. And this is kind of pictorial picture of two sort of representative gauge. For example, as I said, if you solve this for PR and write everything, and then you remove the R part, then you get the gauge, which is called flat gauge, where the spatial curvature perturbation is 0. So you may have the zero slice where the spatial metric is completely unperturbed. In this case, all the fluctuation is encoded in the fluctuation of scalar field. Or you can choose a slice where scalar fluctuations are 0. This is a bit unusual because, for example, in daily life, if you have some field, sound wave or whatever you have, and you can never consider a slice spatial slice on which density is equal. I mean, if you try to do that, I guess your spatial slice would no longer be spatial. So this is a quite artificial slicing, but it works very well in the case of cosmology, especially on a very large scale, because in some sense, if you go on scales much greater than so-called this Hubble horizon scale, actually which determines the space-time scale of characteristic scale of the say gravity, and if you go beyond that scale, then essentially geometry dominates and the matter variable doesn't really play much role. While if you deep so-called inside Hubble's radius, or you just ignore the expansion of the universe like this classroom, then ignoring gravity is the simplest and natural choice. So these two works very well. Say, for example, this flat slicing works very well on inside the Hubble horizon, and this chi equals 0 slice works very well on scale outside the horizon. But this is just sort of intuitive thing, and as long as you're dealing with linear theory, nothing is different. So it's just a change of variables. Yes.
Can this work for the multi-field inflation case too?
Multi-field case, you have many different sort of slicing. For example, you cannot choose total, say, a co-moving slice. This At linear order, you may, but eventually this it becomes impossible. But you can choose, of course, one of the field to be one of the fluctuation of the field to be 0. So you have, but this always exists, of course. Yes. Yes.
So could you explain again how you find gauge variables?
Sorry.
Could you explain again how you find the gauge?
These variables? Yeah, well, as I said, I mean, simplest is you just take a look at this final result. But before trying to combine things, as I said, you have this gauge transformation. I mean, its properties for any canonical variables. So you plug this R or PR and R and chi, yes, into on this equation, and then you know how they transform under gauge. Then, as I said, since we know or we guess that chi should disappear, should be absorbed into other variables, because the other sort of partner has already gone. So then you just look at this gauge transformation property and see if you can construct some gauge invariant combination out of the, say, PR and chi or R and chi. Then you immediately see that this is gauge invariant. So just try, for example, plug this into this equation. Okay, for example, if you plug this PR, then of course CV is PT, so this doesn't matter. CA has this place, and so PR and R gives you this delta or what is it called, unity. So this means that you have the Laplacian of chi. Sorry. No. Laplacian of some variable t. Yes, and then you do a transformation of the chi. You put chi here, and then you have this chi. Yeah? Then you obtain phi prime. Now you have one Laplacian of t and one have the phi prime t, and you combine these two to remove everything. Then you find this is the way to remove the gauge transformation. You see, okay? So this is sort of a simplest, and without noticing that you are fixing gauge, you get gauge invariant things, and everything becomes unique and solvable. Now, from here, of course, I mean, you can just do the standard. There are equivalent sort of a form of a Hamiltonian, of course, because those any system has a canonical degrees of freedom. But so in some sense, if you want to remove this sort of degrees of freedom in the canonical formulation, you can go back to the second order form by solving the P with respect to R prime. So then this would become the standard sort of form, and which is actually like this. This will be the second order form, and which probably you have seen in many places. And well, here the coefficient is 1 because the sound sort of velocity of the propagation is equal to the light velocity. But some people called Garriga and Vilkanov, and some time ago, said that, well, it doesn't have to be 1. Let's introduce some CS square here. And actually it works well. I mean, so there are now many models which has non-trivial sound velocity. But for the moment, in my lecture, I assume C equals to 1, because that's the simplest. But anyway, important point is that if you write in this form, there's no potential term. And if there's no potential term for long wavelengths, which means that if this can be ignored, this is essentially spatial derivative. So if for long wavelengths, spatial derivative becomes infinitely small. So in that limit, actually you don't have any propagation. Means that if it doesn't propagate, it stays constant. or maybe it just depends on time. I mean, and evolution is independent from other parts of the universe. So you have evolution just along single path, and actually in the Fourier equation it's simpler, and then you can simply ignore k goes to zero limit, which corresponds to the long wavelength limit. Then you have at least one solution which is constant. And this is the sort of famous conserved constant modes on scales greater than horizon. There is another one which is usually decaying, because this is the R prime is 1 over z, and this z parameter is equal to a phi dot over h. And if you have a slow rolling scalar field, then the phi dot is usually slow rolling. Hubble parameter also is slow rolling. So it is essentially equal to scale factor. And if it is essentially equal to scale factor, then this 1 over z means that the z goes down. I mean, z grows, and 1 over z goes to 0. So, so this mode corresponds to so-called decaying mode. But again, this may not be true in some cases. And this is something we have to be very careful. So it's true that there exists a constant mode. And this is a very, very general property. And actually, I have assumed a inflationary background, but you don't have to assume inflation. I mean, you don't have to assume anything for any background. And I mean, of course, I'm assuming Einstein gravity. But in Einstein gravity, if you take fluctuations in so-called co-moving slicing, or actually this is a slice where in some sense fluctuations in density becomes minimal. In this slicing there is always a mode which stays constant. Yes, but whether this dominates the other mode depends on your model. And as we said, in the simplest slow inflation model, this is essentially equal to scale factor, so this is decaying, so you can ignore them. But if they varies rapidly, or if they have some very peculiar behavior, then this may not be decaying. Actually, they can grow. And in this case, this mode would dominate your perturbations. So you have to be very careful. Yes. I mean, you have to know how this behaves before you decide whether the constant mode dominates the universe or not. But anyway, so for slow roll inflation, single inflation, this is always true. So this constant mode dominates when it scales is much greater than the horizon, and this simplifies equations considerably. Okay.
So Misao, now
Yep.
we have 5 more minutes. You want to stop here and take
Oh yeah, that's right. Okay. Yes, maybe. Yes, please. Yeah.
So this is time for questions of whatever you want to ask.
Yes, please.
Please.
If you have vector perturbation or tensor perturbation, then can you generate gauge invariant variables by the same way?
Yeah. Again, so since I didn't introduce this basic properties of the cosmological perturbations, I should have told you before. Okay, as I said, there are 3 types: scalar, vector, tensor, and at linear order in Einstein gravity, vector perturbation also has 2 gauge degrees of freedom, and only 2, and no other dynamical degrees of freedom, meaning that vector is pure gauge. So you have 2 gauge degrees of freedom in vector and 2 in scalar. Altogether it's 4, and this is what we have: 4 degrees of freedom in because you live in 4 dimensions, the coordinate gauge degrees of freedom are 4. So this means that tensor perturbations are gauge invariant from the beginning. So you have 2 gauge degrees in scalar, 2 gauge degrees in vector, 0 in tensor. So tensor is the simplest. You don't have to worry about gauge transformation. And vector is also simplest, because it doesn't contain any gauge degrees. So unless you have some non-trivial vector field or some anisotropy of the universe, at linear perturbation order, a vector is always a gauge. Yeah.
So can you go back to slide 10? Slide
10. Yes.
So here you have a few gauge invariant combinations.
Mm-hmm.
So, but here in the combination, the coefficients are fixed completely. But suppose I know the combination, gauge invariant combination, and just write down the action in a gauge invariant way, but with arbitrary coefficient. So what can you do in the case?
You have a suggestion from this part, this so-called kinetic power, whatever you call. I mean, originally it has this formula, P Q dot. For example, in our case, this will be PR R prime. Yes. So of course you multiply P by some factor and then divide by some factor, and you can define some new canonical conjugate. But if you have something from the beginning, then it's simplest to just normalize things into that. And then at the linear level, this is simply you just put this coefficient equal to 1. Yeah. Yeah. I mean, of course, it's your choice. You can do whatever you want, but.
So in your constraint level, Lagrange multipliers
Yeah.
in front of you. In principle, the Lagrange multipliers are arbitrary parameters,
Mm-hmm.
and it's related to the freedom.
Yeah. Gauge degrees of freedom. Yes.
So then like in the gauge theory, can you include it? Gauge parameters and gauge physical parameters explicitly in the.
Oh yeah. Well, so that's the original Dirac method. Yes. So you know constraints, and once you have a constraint, you introduce a gauge condition, which do not commute with gauge the constraints, and this will be the gauge condition. Yes. So that's how you fix things. Yeah. Yes.
My question is about how A and B that function appear in the.
Oh well, as I said, in the end it disappears because this is, as you said, the constraint is 0. I mean, and when so you focus your physics on the constraint hypersurface, then constraint equation just is C equals 0, so the coefficient doesn't matter.
For instance, in the case of gauge theory, you have a Lorentz gauge.
Yeah.
But if you
Lorentz gauge, actually, Lorentz gauge actually still contains additional gauge degrees of freedom, so it's not completely gauge fixing. So it's slightly different. I mean, you could probably do similar thing here, but that only complicates things. We do need to fix gauge in order to arrive at final Hamiltonian. So we don't want any arbitrary other functions. Yeah. So that's the difference. Yes.
This is the last question.
Yeah.
Well, as to the Friedmann problem, the two regions looks causally disconnected at the scattering surface.
Mm-hmm.
But if you go back to the origin, the starting point, physically they are same. So there, if you use some proper lengths instead of ordinary lengths, then the initial two regions are actually same physically.
Oh yeah. So well, this at exactly eta equal to 0. This conformal transformation breaks down because that's the singular point. But as soon as you weigh infinitesimally, then this is okay, right?
Yeah.
Then what people call this as sort of a conformal completion, saying that you add eta equals 0 to this, but it doesn't change any physics. It's just, so you, yeah.
Then you go back to the original coordinates, not
No, well, you want, if you want. But as I said, when you discuss causality, this is most useful. Because if you go back, you don't really see the causality from this equation.
But what I'm saying is the two regions which were causally disconnected at the rest scattering surface, but that if you go back to the t equals 0, then...
No, this is t equals 0, yes? But in conformally squeezed,
right.
or the extent, stretch, sorry, the other way around. So one point is stretched to infinity. That's because a equals 0.
Right.
Yeah. Yeah. If you divide the s squared by a squared, you see that this is when a goes to 0, you are stretching everything.
Okay, then let me test it differently.
Yeah.
Can we really say the two regions were causally disconnected from the beginning?
Yeah. This is what it. I mean, as I said, conformal transformation doesn't change causality. So. A causality which is valid here is exactly valid here too. There's exact one-to-one correspondence. Yeah. So if you have some causal problem in this coordinate, you have a problem in the other coordinates or any coordinates.
Okay. Then you go to the next.
Yeah.
So here you claim that using some inflationary expansion. We could solve the horizon problem.
Yeah, right.
For the current universe.
Yeah.
But if you just simply use that diagram, then what happens to the future universe?
Well, yeah. I mean, so you might see something interesting. Yes. If you wait maybe another 10 gigayears, maybe 100 gigayears. Your horizon becomes larger, and if there's a finite past in the inflation, and then you begin to see what kind of universe we had before inflation. Yeah, but usually the inflation is assumed to be lasting quite a long time, and this number, for example, the number we forgot 60 or 70 is something we require as a minimum, but most inflation model predict at least maybe a few hundred defaults. So it will take a rather long time to see the outside of that horizon.
Yeah, but
eventually, if we are.
Future.
By the way, yes. Another thing. Okay. Yeah. Well, when actually. People say that we are entering the accelerated universe again, huh? Yes, and if this is really caused by cosmological constant, then you just reverse this, the condition to the future. Okay, so instead of having infinite future, you have a finite future. Okay, then you cannot really see the whole universe because now you have upper bound fixed. So if it is really a cosmological constant, or the acceleration continues forever, we only can see whatever the time you wait. We only can see only a finite part of our universe. Yeah, that's the current status.
Thank you very much. So let's finish this session.
Yeah, thank you.